Hello everyone, and welcome to this video on the pullback of one forms. Now it follows on from the series that deals with the push forward of vectors, and the two are related, as you'll see. Anyway, the pullback of one forms is an essential concept in differential geometry, particularly when working with smooth manifolds. A one form is a covariant object that acts on tangent vectors, which are vectors on a manifold, and produces real numbers. The pullback operation allows us to transport, to bring back, to move one forms between manifolds in a way that is consistent with the underlying smooth structure. All right, let's go over here. So what we've got here is a one form here. I'm just going to use this symbol here with the flat head at the top instead of an arrow like a vector, because they're not vectors. Now, one form such as omega f of p, shown at the point f of p down here, so omega at f of p. So here's our one form at the point f of p, is an element of the cotangent space t, the cotangent space to the manifold n at the point f of p. The asterisk up the top there indicates it's the dual space or the cotangent space. All right, so here's our manifolds. Here are two manifolds M and N. We have a point P on M, and we have a map that takes points on M and maps them to points on N. And in particular, here's a point P here, which is mapped to the point F of P. Hence, we have the point F of P up here in the cotangent space to the manifold N at the point F of P, and our one form at that point. Now we have a vector tangent to the point P on the manifold M. It exists in the tangent space of manifold M at the point P, and we have that induces, and we have a vector at that point. And this vector we push forward to the tangent space of the manifold N at the point F of P, thanks to the map. F is a map from M to N, and the mapping that between the tangent spaces that is induced by the Jacobian at the point P of the mapping F acting on the vector V. So we push this vector V forward to this here, F subscript star at the point P of the vector V over here. So this is the push forward of this vector here. Okay, and that's all been covered in the push forward of vectors in the last 5 videos prior to this. Okay, so the tangent space, the cotangent space at the point P, or the dual space to the manifold M at the point P is shown here. Now, these cotangent or dual spaces occur at the same point here. They're only separated in my diagram here for the purposes of exploring the concepts and to give you a visual picture to think of. They are not separate up here away from the manifold or anything of the sort. They are actually at the point F of P, and they're coincident at that point there. If I were to draw them together, my diagrams would be very, very messy. So the only reason they're up here like this is just to show you what's happening in the cotangent spaces here, and so as not to make my diagram here of my tangent spaces to the manifolds M and N very messy. Right? That's the only reason it's there. And I'll just follow that in all these pullback videos. I'll have the cotangent space separate up here so you can see what's happening within it. But remember, they are coincident at each of the points P and F of P here. All right, so let's move on. So that's what we have. So we have the map between the two manifolds, M and N. F is a map from M to N, which takes points on M, maps them to points on N. And we have, from the tangent spaces here where there's a vector, this induced mapping using the Jacobian evaluated at the point P, acting on the map F, acting on the vector V. All right, so let M and N be smooth manifolds, and let F be a map from M to N, be a smooth map between them. Smooth, so continuous, and no sharp turning points, no points where the gradient suddenly changes sign. For any point P belongs to M, the tangent space TPM is the vector space of all tangent vectors at P, which represent directions in which the manifold can be locally traversed. So just a bit of revision there of tangent space. A one-form omega on N is a covector field, which means it is a smooth map that assigns to each point F of P belongs to N, a linear map omega F of P, which is a map from the tangent space to N to the reals. So in other words, a one form takes a tangent vector. That's what this mapping here is indicating, a tangent vector from the manifold n at the point f of p, and produces a real number, hence r. So the action of a one form omega on a tangent vector v equals, if we write out this component form vi partial xi, is given by omega acting on v is omega I dxi. Okay, that's the one form. Here's the vector here. Now these components we can pull out, multiply them together, so omega I vj, and then the Kronecker delta applies between the basis one form cxi and the basis vectors partial xj here. Kronecker delta applies. When j is equal to I, we have omega I vi. And this is a scalar. This is a number once you have evaluated at a particular point. All right. We have seen how we can push vectors forward from m to n using the map f, but can we also, okay, so we pushed it forward here. Here's the induced mapping here. Okay, remember the Jacobian of f acting on the vector v. All right, so the Jacobian matrix of f evaluated at the point p multiplied by the vector v. All right, so that's a mapping from the tangent space of m at the point p to the tangent space n at the point f of p. So it's taken this vector here, pushed it forward. The question now is, okay, we have a one form acting in the dual or cotangent space to n, but can we pull this one form? This video is only focused on one forms at the moment. Can we pull that back to this point P here? Okay, and it will turn out, thanks to the mapping F, that we will, and that's the focus of the rest of the video. So we've seen how we can push them forward under the map F, but can we also pull one forms back from N to M? So that's the goal here. All right, now a one form omega can be locally written in terms of a basis of the cotangent space. Remember the asterisk up the top indicates a cotangent or dual space. F of p n as omega is omega 1 dx1 plus omega 2 dx2 plus blah 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 omega n dxn, where dx1 dx2 dxn are a form of basis of one forms and omega I are smooth functions. All right, now the pullback of a one form omega on n, that's taking it from the cotangent space at n to the cotangent space at m via a smooth map f is a map from m to n, is a one form on m. Okay, so when we pull that omega back that was in the previous diagram, we'll get another one form on m. This new one form, denoted f star omega, is constructed in such a way that it transforms consistently with the map f. So for each point P belongs to M, the pullback one form f star of omega at the point P is defined as f star omega at the point P, acting on the vector Vp, because remember one forms take vectors as their arguments to produce the scalar number, is the same as the one form evaluated f of P acting on f star Vp, the push forward vector. Okay, remember I was showing that in the diagram before. So f star omega acting at the point P acting on Vp is omega f of P acting on push forward vector f star Vp, where Vp is an element of the tangent space of the manifold at P, is a tangent vector the point P belongs to M. F star Vp is an element of the tangent space to the manifold N at the point F of P under the map F, is the push forward of the tangent vector via F. And omega f of P is the one form evaluated at the point f of P belongs to N. So down here we have our dual or cotangent space to the manifold N at the point f of P. Okay, we have our one form evaluated at that point, and you'll see later how the map F comes into that to take it from the coordinates here to the coordinates over there using the map F. And then when we do pull that back under this pullback map, we get a one form over here. Okay, so that pulls this one back to here to give us a one form on the manifold M in the cotangent or dual space in the manifold M. Okay, so in other words, the pullback f star omega takes a vector, tangent vector P belongs to M, applies the push forward f star to map the tangent vector to the corresponding vector on N, and that's the subject of all the previous videos on the push forward, and then applies the one form omega to this push forward vector. Okay. Now the pullback operates in the following steps. One, push forward of tangent vectors. Okay, so the smooth map F that maps M to N induces a push forward F star P, is TPM to TF of Pn, which takes a tangent vector Vp belongs to the tangent space at the point P to the manifold M P, and gives a vector F star via P that belongs to the tangent space to the manifold N at the point F of P at the corresponding point F of P belongs to N. Yes. Application of the one form. Once the push-forward vector F lower asterisk Vp is obtained, we evaluate the one form omega at the point F of P belongs to N and apply it to F star via P. This gives a real number. Okay, because remember, one forms acting on vectors produces a real number. The resulting pullback, the pullback F star omega, is defined in such a way that for each tangent vector Vp belongs to a tangent space of manifold M at the point P, the pullback one form, F upper asterisk omega at P, produces the same real number omega produces at F of P. All right. So F star omega at P, when it acts on a vector, produces the same real number that omega produces at F of P. All right, so F star omega at P acting on the vector Vp is equal to omega F of P acting on the push forward F lower asterisk Vp. All right, these two things produce the same number. And that's the important thing. When you think about it, F is taking us from manifold M to N. So when we apply that under the map, see how F is involved here? When we apply that, what we're really doing is taking those coordinates on M, we push them forward to N, and then we're going to use them to go back because they're the coordinates from the first manifold M. All right, so let's go over. So in other words, under F, we're taking our coordinates from here forward to here. Okay, so when we pull them back, we've got our coordinates from M already, and that takes us back here to the cotangent space at M. You'll see that with some examples. All right. So coordinate representation. In local coordinates, the map F from M to N is given by a set of smooth functions. F of X is F1 of the coordinates on M, F2 up to Fn, depending on the dimension. All right, where x1, x2, xm are local coordinates on M, the first manifold, and Fi are the coordinate components of F on N. Let omega equals omega j, subsequent j, dz, upper contravariant j, be a one form on N, where z1, z2, zm are local coordinates on N. That's on N, the second manifold. The pullback omega via F is F upper asterisk omega is omega j. And just to emphasize that we've used the map F to take coordinates from M over to N. Okay? That's what that's trying to emphasize there. And then we have the Jacobian here, okay, expressed into, and then dxi. Okay, so the total differential here. Okay. Partial fj, partial xi, dxi. Okay, where dfj, dxi is the Jacobian matrix of F, and dxi are the coordinate one forms on M. Okay, so we push them forward to N. Be better with an example. Okay, so here's an example. Let's consider an example where M is the R2 Euclidean space, two-dimensional Euclidean space, and N is also R2. And the smooth map F that maps R2, two-dimensional Euclidean space, to two-dimensional Euclidean space is given by F of xy is F1 of xy, F2 xy is x squared minus y squared, and 2xy, and that's Z1 and Z2. So this map takes a point xy and M and maps it to a point Z1, Z2 equals the F1, F2 in N, where Z1 is x squared minus y squared, Z2 is 2xy. These, or F1, F2, the component functions. Let's say we are also given a one form omega equals dz2 on R2. Okay, so dz2, the 2 not being a square, but just the second coordinate. On N, we have Z1, Z2. Okay, the goal is to compute the pullback of this one form, this one here, omega, via the map F, denoted by F star omega, F upper asterisk omega. Okay, so we want the pullback of this, which is on N, back to M. Okay. All right, so let's remind ourselves the pullback F upper asterisk omega is omega j F of P at the point f of p, because remember we have to evaluate at the point f of p. We have to evaluate at the point f of p, our one form. And then we have the Jacobian, okay, which was this part here was the push forward vector. Notice all these differentials here. This is when you expand out total differential. So our one form at f of p omega is omega 1 f of p dz1 plus omega 2 f of p dz2. Notice this part was 0. So there was no part there, it was just this. And this factor omega 2 at f of p is just 1. This first example is just keeping it simple. The next video that follows will contain some other examples where these are not 0, these coefficients. And so we just simply have our one form at f of p is dz2, the second coordinate. Okay, so here we are. Omega f of p is dz2. Okay, cotangent space at n, cotangent space at m, and we want to pull this one back from n to m, from the cotangent space n to the cotangent space m at the point p. So f star omega is, here's our rule again. Okay, here's our here. Now this one, the component functions here are the first component functions, which as we've already discovered up here, they're 0, so that's simple enough. I just included for completeness because I could have not bothered with this, but I just want to show you this will be 0 because remember up here there was no dz1. Omega 2 comes into operation now, so df2, partial f2, partial xi, dxi, okay, and that's non-zero. So all this here tidies up to 0 plus partial f2, partial xi, dxi, okay? And remember, if f2, if you remember, was 2xy. Yep, f2 was 2xy. So in this particular case, our pullback f star omega will be partial f2 of xy, partial xi, dxi, and then we're going to expand that out for the xi, okay, 1 and 2 because we're in 2 dimensions. So we'll have dx and dy, okay, these terms here, and then, okay, so we're going to take the partial derivative with respect to x of f2 here, dx, then the partial with respect to y of 2xy dy. Okay, we get 2y dx plus 2x dy. So the pullback of omega via f is f star omega is 2y dx plus 2x dy. So the one form dz2 in the cotangent space to n at the point f of p, dz2 becomes in the cotangent space m at the point p becomes this object. Okay. So geometrical intuition. So the pullback of a one form geometrically transports a one form defined on the manifold n back to the manifold m. Intuitively, this allows us to measure the rate of change of a function or apply the differential form on the new manifold m, while respecting the way m and n are related by the map f. All right, why it's useful. So the pullback of one forms is useful in many settings in general relativity, where one forms represent physical quantities like the gradient and the gravitational potential. In electromagnetism, where one forms are related to electromagnetic potential and its field strength, and in differential geometry to move differential forms between manifolds, which is crucial for defining integrals on submanifolds and relating different coordinate systems. So in summary, the pullback of a one form takes into account the geometry of the map between manifolds and provides a systematic way to transport one forms from one manifold to another. All right. And just to remind ourselves, this, stop hiding that now. I don't think there was another slide, was there? No, I'll bring that back. So here's a whole picture of the situation. So we've got our two manifolds, M and N. We've got a point P on the manifold M. We have a vector at that point, which exists in the tangent space to that point, tangent space to manifold M at the point P. We have a map between the two manifolds M and N, which is a map from M to N, which takes points on M and produces points on N, maps into points on N. And then we have here our vector V can be pushed forward under this mapping between the two tangent spaces, dp f of v, and that was the subject of all the 5 videos on the push forward of vectors. And that's a mapping from the tangent space to M at the point P to the tangent space to N at the point F of P, which gives us this vector over here, F lower asterisk at point P of V, okay, here, and F of P, and then each of these spaces has a cotangent or dual space drawn up here not because they're actually physically separate or in any way like that, but they occur at the same point. But to prevent my diagrams from getting overly messy, you can imagine if I tried to combine all this together, the diagrams would be unreadable. All right, so up here we have one forms exist in the cotangent space to n, and a particular one form at the point f of p under this map, from p to f of p. So here's our one form there at f of p, and we want to pull it back to find its form over here on the other dual space or cotangent space. Okay, so this object here will give us this one form over here. All right, and that's been the focus of this video. Now, next video will contain some examples and a few more definitions as well. And then we'll have a look after that at the pullback of two forms, and you'll see how the pattern works. All right, I hope you find this useful, and I'll see you in the next video. Thank you for watching. Please push the like button and subscribe if you will, and I look forward to seeing you in the next video. All right, thank you everyone. Bye.